Hello, welcome to some chemistry concepts. My name is Len, and today, although to be honest this will probably be the only day, we will be going over an introduction to solubility rules. To precursor, we need to understand polarity rules and why things may or may not be soluble. Generally, polar molecules, asymmetrical molecules like salt, will dissolve in other polar molecules like water, and non-polar molecules like cooking oil, gasoline, and acetone will do the same with other non-polar substances. Of course, it can get a little bit more complicated than that when determining what is polar and non-polar. I'll leave a few helpful videos on polarity in the description box. Now, when referring to solubilities here, we will only be referring to if the substance dissolves in water solvent, otherwise known as aqueous solutions. The reason why a nonpolar molecule would not dissolve in water is because the molecules are not attracted to each other and instead they repel each other. But there's a lot of different factors that go into whether something is soluble, and mostly through experimentation we know these rules. So the solubility rules generally goes like this. All group 1A salts and ammonium salts are soluble. Chlorides, bromides, and iodides are soluble with the exception of silver, mercury, and lead. Fluorides are soluble with the exception of alkaline earth metals. Nitrates, chlorates, hypochlorates, and acetates are also soluble. Sulfates are soluble with the exception of calcium, strontium, barium, silver, lead, and mercury. Hydroxides will always be insoluble with the exception of rule number 1, which takes priority over this rule. Other exceptions are calcium, strontium, and barium. All other anions will be insoluble, but rule number 1 still takes priority. When you think of it, alkali metals and ammonium can only bond with one other ion with their 1+ charge. That guarantees a polar molecule, if you remember that polar molecules are asymmetrical. Rule number 3. The reason why fluorine is so special when it comes to its solubility, separate from the other halogens, is because fluorine is super electronegative and will not want to give up the ions that it is attached to. Alkaline earth metals have 2 valence electrons that they can give up, and the trait of 2 electrons makes that ionic bond with another ion much stronger, as the greater charge of 2+ has a stronger attraction than, say, an alkali ion with a 1+ charge. Thus, it'd take a lot of energy to separate ions that are strongly attached to each other. As for rules 2 and 4 through 7, there's not really as easy of an explanation. In general, a substance is soluble if water can easily separate their ions apart from one another. And this means that the substances which are insoluble are too tightly bonded together, and that water can't pull them apart. There isn't a clear and easy pattern for memorizing those trends though, so it's just better to memorize the solubility rules as they are. So let's classify each one of these as either soluble or insoluble with some practice problems. You probably haven't memorized them yet, but I hope enough practice and panic about the upcoming test will help you memorize them. Starting with sodium bicarbonate, we know that sodium is an alkali metal, which means that it has a 1+ charge. Carbonate is a polyatomic ion with a 2- charge. With that information, we can determine that there will be 2 sodiums to make up for that 2+ charge, and there will only be 1 carbonate. Because sodium is a group 1 metal, we can look at rule number 1, and because carbonate is an anion that wasn't listed, we can look at rule number 7. Rule number 7 says that carbonate will be insoluble, but remember that rule number 1 takes priority. So this means that this substance is soluble. For ammonium sulfide, ammonium has a 1+ charge, and sulfide, looking at the periodic table, has a charge of 2-. So that means that there will be 2 ammonium ions and only 1 sulfide. Because of the ammonium, we can look at rule number 1, and we can see that all ammonium salts will be soluble. For calcium fluoride, we know that calcium is a group 2 metal and that fluoride is a halogen, meaning that it has a charge of -1. So there will be 2 fluorides. And because of this fluoride, we can look at rule number 3, which says that fluorides are soluble, except with alkaline earth metals, which are group 2A, which is what calcium is. So that means that calcium fluoride is insoluble. For lead bromide, bromide is a halogen with a 1- charge, and because of the 2+ charge on lead, there will be 2 bromides and lead bromide. And because of this bromide, we can look at rule number 2, which says that bromides are soluble. However, there is an exception with lead, which means that lead bromide is insoluble. Alright, let's try to go through these using double replacement problems. Let's see if the reactions of these aqueous reactants form aqueous or solid products. Remember that aqueous means that the substance is dissolved and ionized in water. So for barium hydroxide and copper acetate, I'll just go ahead and make this quicker and tell you that this is what barium hydroxide and copper acetate looks like. Barium has a 2+ charge, and copper in this situation will have a 2+ charge as well. Hydroxide will always have a charge of 1 minus, and so will acetate. So that means that there will be 2 hydroxides and 2 acetates paired with barium and copper. In a double replacement equation, we can just switch the anions. So that gets us barium acetate and copper hydroxide. Because of the acetate, we can look at rule number 4, and because of the hydroxide, we can look at rule number 6. So rule number 4 states that all acetates will be soluble, which means that barium acetate will be an aqueous substance. For copper hydroxide, however, copper is not one of the exceptions that makes hydroxide soluble, meaning that this is a solid product. And just the last thing, an insoluble product in water will form a precipitate, which might take form of a cloudiness in the substance, or debris floating at the top, or sinking to the bottom of the solution. And that's about it. This screencast could not happen without the help of Miss Wilson, my sophomore chemistry teacher, and the textbook equivalent of a LASA chemistry packet, generously created by Miss Moore, Mr. Olenzizek, Miss Willie, and Miss Wilson again. Graphics were drawn and provided by myself, and sample chemistry questions were taken from the before-mentioned LASA chemistry textbook. Thank you so much, LASA chemistry teachers, and thank you, viewers, for tuning in. Let's hope this little lesson helped with your chemistry homework.